this tape, as it moves, keeps on going in a straight line, but the tension on the string that I am providing, that I'm pulling back, as long as I keep holding on to it, it keeps changing the direction that the tape is moving in. The tape keeps wanting to move out, keeps wanting to move in a straight line tangent to the circle that it's inscribing. And so that's some geometry for you, all right? It keeps wanting to move in a straight line, and I keep pulling it back from that straight line. But if I release the string, the tape ends up moving in that straight line that it was previously moving in. So we can think of it as this tape continuously being corrected in its position by the string that it's attached to. Okay, so I have linked from, I believe from the assignment, correct me if I'm wrong, I linked this interactive. So I'm going to demonstrate the interactive, but I know there's some lag time on Zoom, so you may find it more helpful to bring up this interactive on your own. And what we're seeing here is uniform circular motion that I just demonstrated. And there's nothing particularly special about this just yet. We can bump up the speed. We see that that increases both the acceleration and the net force. Let's bring the speed back down. We can increase the radius. If we increase the radius, what is that doing to the net force?
Decreasing.
Decreasing the net force. All right, so I'll make my video nice and big now. So if I decrease the radius, I know this is harder to do. It's harder to keep it in motion than if I increase the radius. Now I have to exert less force to keep it in motion. All right? There is more force required because this is a higher acceleration. So radius has an impact. If I shorten up, as I showed you, the acceleration, that requires more force to keep it going. So we're seeing that there's a relationship between speed, acceleration, radius, and force. And of course, there's a relationship with mass. As we increase mass, then force must increase. If instead of a tape ball, or instead of tape, I had a ball on here, or I attached like my cat, that would increase the total amount of force that I would have to use in order to spin around my poor cat, who would be meowing the entire time, all right? So you can play around with mass and radius and speed and see how that impacts force and acceleration. Now that's the calculation piece. Now the vectors are what is really going to be very interesting for us to appreciate. What do you notice about the velocity vector? About the direction the velocity vector is pointing in? Go ahead, Aisha. Are you unmuted because you want to mention that? Okay. What do you notice about the velocity vector? Well, you were unmuted, so I thought you wanted to respond.
It's pointed downward. That's all I know.
It's pointed down.
It's going around in a circle.
So the velocity vector, this is the tricky part, right? Is the velocity vector pointed out? Because, you know, when we spin this thing around, it's pulling on us. It feels like it wants to go out. But does it want to go out? Where does it want to go? Where does this, what's the velocity vector pointing to? If I pause it, what do we see about that? Where is that velocity vector going?
I still say downward. Oh, and wait. Towards gravity?
It's actually going in a straight line. Okay?
Oh.
So notice that the velocity vector is pointing in a straight line. It's not pointing in the direction it ends up going. Because what's happening here is that the velocity is constantly changing.
Okay.
All right? Because the velocity vector is pointed in this direction, but it's actually traveling around the circle. What's happening is that this velocity is constantly changing, is being pulled into the middle by the force that you are exerting on it with the string. And so what that means is that the acceleration vector, and let me change this so that we see this a little bit easier here. What it means is that our acceleration vector is pointed directly towards the middle of the circle. Because the force that we are exerting on the object, in the case of my tape and string, the force is coming from the middle. And so that acceleration is pointed towards the middle. Remember, acceleration is a change in velocity. So that changing velocity is actually happening towards the middle. We'll pause it so we can look at this in a little bit more detail. This is where the ball wants to go, this way. But the ball's really going this way because the force is pulling it straight in towards the middle. Okay? So we can see this again where the acceleration's pointed towards the middle and the velocity is trying to just move it in a straight line. And it's this push and pull between where the ball or object wants to go versus where you're pulling it. And that's why it requires constant force. Right? If we stop applying that force, bye-bye tape. Oh, I'm sorry, I just hit my dog. That's okay. Poor doggy. He's okay. But the tape will just want to continue going in whatever direction it's going. Questions about how the acceleration and the velocity vectors? All right, feel free to ask in the chat. So going back here, we should be able to now answer number 4 about an object moving uniformly in a circle. Can have a constant something, but a changing something else. And the direction of the velocity vector number 5, you can select more than one of those. Obviously, circling might not be the best option if you want to highlight, or you can change the blank to be all the ones that apply. And I will let you answer numbers 6 and 7. So I will give you, let's say, 3 minutes to work on numbers 4 through 7. And then I want you to try, if you get done with those early, try number 8. You've got a formula here to help you. I also give those formulas up here. All right, so work on numbers 4 through 7. If you get done before my timer goes off, then start on number 8. Questions? Okay, so let's take a look. That's why I want you to have this animation up, right? Where's the net force? What represents the net force in this animation? What symbol represents a net force in this simulation? The location of the net force, I should say. Right, middle of the circle. That plus in the middle of the circle represents the location of the net force. So is the velocity vector in the same direction as the net force? Is it the opposite direction as the net force? Or is it some other relationship? Because there is a vector that is pointing towards the net force. Which vector is pointing towards the net force?
The acceleration.
Absolutely. The acceleration is pointing towards the net force. But the velocity vector is actually perpendicular to the net force. All right, there's a 90-degree angle there. Right? And that 90-degree angle is going to be very helpful when we start calculating, because that's our triangle.
Does that mean there was only one answer to question 5?
Correct. The only one that was correct was A. Okay? The velocity and the net force are perpendicular to each other. So, true or false, number 6. The direction of the velocity vector of an object at a given instant in time depends on whether the object is speeding up or slowing down.
False.
Why do you say false?
Because wouldn't it depend on just the direction the object is moving? Yeah.
So the direction of the velocity vector, let me demonstrate here for a second. So ignore the string, all right? This is just moving along here. And if I speed it up, right, the velocity vector is pointed in what direction? From your perspective, what direction is this?
Positive.
What?
Never mind.
Right or left?
Right.
Okay. If, however, I go fast and then slow it down, what direction is the velocity vector?
Negative. Left.
Right?
Still right.
What?
Good. Because the velocity, right, is a measurement of both speed and direction, okay? It's still moving to the right, and it's still moving with a positive speed. Now, the velocity vector would switch to the left if I start moving it to the left. okay? So let's go back. The direction of the velocity vector of an object at a given instant in time depends on whether the object is speeding up or slowing down. So what is that, true or false? The direction of that velocity vector.
False.
Yep.
Well, I had the answer right. Wrong explanation.
That's why I don't like true false questions, because you got a 50-50 shot and it doesn't actually tell us anything. So, but anyway, yeah, that is false. All right, for an object moving in uniform circular motion, the velocity vector is directed, and I did help you out on this in the explanation to number 5.
It looked like it was outward, so I said B.
So let's see what out looks like. So out would be that direction, right? The net force is here, out would be there. In would be the acceleration vector. The acceleration vector is pointed in, but the velocity vector is neither pointed in nor is it pointed out.
That's why I just said A, even though I didn't know what you meant by tangent line.
Ah, so you haven't gotten to that in math yet, huh? All right. So a tangent line drawn to a circle is going to be at a 90-degree angle with the line that you draw towards the middle of the circle. Which, of course, I don't expect you to understand from me just saying that.
Oh, you mean like when you draw a triangle from a circle?
So what is the easiest one here? I guess that one's not bad. Oh, great. PNG. Of course, it's transparent. Here's the center of the circle. And if we draw a line, so what do we call this measurement here? From the center to any point along the circle?
Radius?
That's the radius, good. So if we draw a line equivalent to the radius, and then we make a 90-degree angle, this is the tangent line. This is the tangent, the line tangent to the circle. So if you picture the tape ball right here, and here's the string, the tape ball wants to go in this direction right here. It wants to go tangent to the circle, and if I let it go, if I let the string go, it will continue moving in this direction. But as long as the string remains connected and there is a net force applied to that string, then the tape or the ball will travel along this circular path. Okay, so this is where the velocity vector is pointing. This is where the acceleration vector is pointing. The resultant motion is inwards along this circle. Questions about that? This is not easy, especially since you're not familiar with tangent, not just yet, but that's what's happening geometrically. Okay, so let's go through number 8. All right, average speed equation to determine the speed of a rider on a carousel ride that makes a complete revolution around the circle. We're given a diameter, and we're given the time that it takes that rider to travel through. So, which equation are we going to be using? Which equation are we going to use?
Both, right?
Well, sure, but what both? Which one? What equation are we going to use? This is not a
Or
hard one.
average speed.
Yeah, all right. So can you read that? Can someone read that so that I know that you know what some of these things mean?
2 times pi times radius over time.
Excellent. So 2 times pi times radius over time. All right, 2 times pi. How many significant figures do we have in our numbers here? Do we have 1 significant figure? Do we have 2? Do we have 3, 4, 5? What do we have? Thank you, Angela. We got 3 significant figures. All right. 3 significant figures, so I don't have to write 3.14159, blah, 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 blah. I just need to write 3.14 for pi. Okay, because I only have 3 significant figures, so that's all I need to keep. 2 pi times the radius. How do I find the radius? They gave me diameter.
Divide by 2.
Divide what by 2?
The diameter.
Thank you. So 24.6 meters divided by 2, right? And all of that is going to be over what? Two pi r divided by
Time.
13.4 seconds. Now you should see before you do any of the math that we have meters on top and seconds on the bottom. What is that going to get us? If we have meters per second, what kind of thing will that get us?
Velocity.
It'll get us a velocity or a speed, right? Velocity if we have a direction. We don't really have a direction because right now we haven't talked about that piece yet. We've got a speed though. Okay, so 2 times 3.14 times 20, so let's simplify this here. 2 times 3.14 is 6.28. I want to see you do the work in the way that you do the work, not the way that I do the work, please. Times 12.3, because that's 24.6 divided by 2. So we've got 6.28 times 12.3 meters. And then we're dividing that by 13.4 seconds. All right, and I see I have received an answer or two here on the chat. We get, I am going to do incorrect significant figures and make sure that you guys do the correct significant figures. So 6.28 times 12.3 is 77.244. That is incorrect significant figures. I want you guys to correct that. And that ends up with, and I'm going to say approximately, because I want to see correct significant figures, somewhere around 6 meters per second. It's pretty fast. I don't know that I want to be on that carousel ride that's moving 6 meters per second. But it's a pretty fast ride. All right, that's about 20 feet every second. So, questions about how to do A. All right. Then I will leave B up to you. Number 9, we have a roller coaster car that is traveling over the crest of a hill and is at the location shown. We're looking at the side view. Now, I know it's hard to draw an arrow on this diagram. You could probably find a way. Where there's a will, there's a way. You can also just say the direction of the velocity vector, where the velocity vector would be pointed. It does not show you where the roller coaster car is coming from or to. You can make an assumption that it's moving clockwise. So if it's moving clockwise, where is that velocity vector? You can answer either in the comments or by unmuting yourself. Don't everyone answer at once. What direction is that velocity vector? Thank you, Vivian. I agree, to the right. Directly to the right, because that's tangent to the circle. All right, that's where that geometry comes in. Okay, accelerating objects are, choose the one most inclusive answer. What that means is choose the answer that includes all of the correct answers. All right, I am going to let you answer that because that is a review. Identify the 3 controls on an automobile that are responsible for causing the car to accelerate. Remember, acceleration is not just about speed. It is also about what? Acceleration is not just about speed, it is also about direction. Thank you, Angelina. Okay, so then you have some multiple choice questions about acceleration and circular motion here, right? So let's go over a couple of these and then, yeah, we've got a couple minutes. So a car that's moving in a circle at a constant speed of 30 miles per hour in a circle, we know acceleration has to do with both speed and direction. So is it accelerating? If it's moving in a constant speed but in a circle, is it accelerating? Not changing speed, but it is changing direction, so is it accelerating? My arm is getting tired.
You're accelerating, right? Because you have that vector pointed towards the middle.
Yep. It is absolutely accelerating because its direction is changing. If its direction stops changing, right, that means that it will just keep going in a straight line.
So it's E.
I didn't say what it was, but it's not E. And I'll let you figure out why it's not E. Number 13, an object that is moving in a circle at a constant speed has a velocity vector that is directed where? We just talked about this. Where is that velocity vector? Inwards, outwards, or tangent to the circle?
Tangent.
Say that louder.
Tangent.
Yep. So one more time, looking at this, we see the velocity vector is tangent to the circle. And what direction is the acceleration vector in?
Inwards.
Inwards, beautiful. Finally, we got 14 and 15. 14, an object moves in a clockwise direction around the circular path as shown. 3 points, A, B, and C. Draw a straight line vector arrow in the direction of the velocity vector for each direction, all right? So you can do this in any way you'd like. If you'd like to sketch this on a separate sheet of paper and scan it, take a picture of it. And then draw a straight line vector arrow in the direction of the acceleration vector and label that as A. Again, that animation is really gonna help you out. Finally, number 15, an object that is moving in uniform circular motion will definitely have a large acceleration if it's doing what? Could there be more than one correct answer to this?
Can it be all of them?
It could be, as long as you can justify your answer.
No,
So
could
you
it
have
be
to
A or
explain.
C?
Say that again.
I would have said A or C.
Okay. Just as long as you justify your answer. So I'm asking you to justify for number 15. Have a wonderful day. I will see you tomorrow, hopefully for some yoga in the morning.